it anyway. So, hopefully, is our next guy ready with his tight t-shirt?
We can't stand the suspension.
I know. Oh, and I fell for that one. I was going to say, put it in there and just hook me off. And I was going to say, it's
you
just...
know, there's probably a reason why they stopped me doing your job.
Well, see, I feel like Darth Vader, and Tamanja's clearly the Emperor there, isn't it? She's still got it. She doesn't even need a lightsaber. She's still the master. So, are we ready? Next up, we have Leon. So, I'd like a warm round of applause, please, for Leon, everyone.
Right, well, hello, my name is Leon. I'm a PhD and I research hypersonic aerodynamics, which basically puts me in the business of keeping rockets in the sky. And today I'm going to talk to you about something completely different. Today I'm going to talk to you about why we care why insects fly. But before I do that, I have to tell you two very special things about insects. Special thing number one, insects are very tiny. By being very tiny, this means to them that actually air seems a lot thicker than it does for us. So if I were to drop a cockroach from a plane, it wouldn't physically be able to fall fast enough to die when it hit the floor, because the air is so thick that it can't, the drag is high, it falls very slowly. And this is the same sort of reasoning behind insects being able to walk on water. Now, special thing number two is that insects don't actually fly like anything else that flaps its wings. Most birds and things, they sort of fly like they're doing butterflies, sort of like this really through the air. Right? And you can model this kind of well if you approximate them to airplane wings. Insects, when they're hovering, they fly like this, right? Now specifically, what they do is they have their wings angled like this, and they throw them up against the flow like this, and then they'll bring them back and throw them up against the flow. And they'll do this over and over again, right? And actually, when they throw their wings up like this, it stalls their wings. Now, stall, traditionally for a plane, is really bad. Right? It tends to land the plane very quickly, and it takes a long time to pick up the pieces. Right? And so, because when you stall the wing, it actually stops generating any lift. So it comes as no surprise when people try to model insect lift, you know, the way they fly, as an aeroplane wing, actually they got a really bad answer. And the reason they got a bad answer is there's a subtlety to stall. And it's when stall just starts, right, you actually generate lots more lift than you normally would over a wing. Yeah? But on a plane, this is fairly academic, because for a second you generate more lift, and then you stall, and for the rest of the time it takes you to fall to the ground, you generate more less. Right? This is quite bad. But insects, you see, a plane has its wings fixed, and the plane moves forward. But when an insect hovers, it stays still, and it moves its wings. And this allows it to do something very clever. See, what it does is it starts the wing coming forward, which is stalled because it's flat against the flow. And as it's coming forward, the stall starts, right? And this generates lots more lift than it normally would. So it brings it forward, the stall starts to develop, and you're just about to get the bad bit stall, and it stops. And it turns around and goes back and does the same thing. And this is why it allows the insect to kind of weave together all the really good bits of stall. Right? And that way it generates lots more lift. And this is really clever, and you can actually apply this to lots of things. You can apply to helicopters, and helicopters fly better. And people are really interested because people want to build lots of swarms of flying robots and things, and they want to find tricks to help them fly better. I'd love to tell you more about these tricks, but unfortunately I've got 3 minutes, so I'll stop. Thank you.